Okay, Assalamu alaikum students. This is your ODL lecture number 1 for electric machinery fundamentals for session 2020. Actually, the lecture went through, but the recording was not done on MS Teams. So I'm actually just recording this, just a brief overview. Actually, it was just an introduction to the course and a little bit upon the DC machines or DC motor that we have already done in your FSC or A levels. So we are just going to give a little bit like 20, 30, 30 minutes on this one. But before I move on towards the overall DC motor and all that stuff, the course outline, you have it available on your LMS. So just a brief discussion of the all 4 CLOs. If you go with the CLO1, which is actually the applying the concepts of magnetic circuits for the performance evaluation of electrical machines, that actually goes on with the magnetic circuits, as you all know. And magnetic circuits, you remember it, they are going to be an integral part of all the machines, since I have also told previously that any electrical machine which is having any rotation, this means certainly that there is some electric current involved, and because of that current or due to any other current, there is a magnetic field involved. So whenever there is going to be any motion involved, either it's a motor or a generator, you are always going to have magnetic circuits. And magnetic circuits are those circuits which are going to have a flow of electric and magnetic current there. So magnetic circuits are going to be discussed in CLO1, which will approximately going to take 1 or 2 weeks over here. In fact, maybe 2 weeks plus. So whatever machine we are going to discuss in this course, we are going to talk on magnetic circuits first. And since magnetic circuits are here, so we will talk about how and which materials are better for magnetic circuits. So this will be a total concept on how flux is going to flow, and I hope everyone has an idea the difference between the flux phi or the flux density B and the flux intensity H. So hopefully you can revise these 3 parameters, and we will discuss that in the next lecture when we formally start the magnetic circuits topic, that is chapter number 1 from Chapman, which is our course book. Then if you move on towards the circuit CLO2, which is about the DC machines, and many of my colleagues and peers, they also have this counter argument that DC machines are getting obsolete, but the basics of any machines actually starts from any DC machines. So that's why this DC machine is still a part of our course, and this is going to be covered from chapter number 7 and chapter number 6 from our Chapman, and certainly some more notes which are related to our windings of our DC machine. I will discuss DC machine just today also, again just for a little brief reminder for your previous classes you have done through your machines. And then the third CLO, this is related to transformers and three-phase machines. Now, transformers are not mechanical devices, but they are a very integral part of our power systems, and all the power that arrives at our homes or industry, that has to travel through transformers. So transformers are very, very important elements of our power system. And you all know, since AC is the actual voltage available at our homes or load centers, so transformers are actually the voltage conversion devices. So they are actually either stepping up or stepping down. So we are going to go a very deep analysis on transformers. We will draw its equivalent circuit. Now, the word equivalent circuit may be a little new for you, but remember, in electrical engineering, whenever we are talking about any device, we have to model that device. If you have supposedly a fulcrum or a pulley, then you can model it also in some electrical domain. If you have some transformer, you have to model it into some electrical domain using, of course, some passive elements which are R, L, or C, or maybe if there is some other object, you can have any active device also involved over there. So modeling or equivalent circuit of any device is the core of electrical engineering, and we are going to do that lot in our course of EMF over here. Then in CLO3, we are also going to discuss the induction machine, which is actually the workhorse of any power being consumed in our industry. In fact, a little value, if I quote over here, that almost 90% of the power, not 90 actually, maybe it's a little large or hypothetical value, but a 70% to 80% of the value of power being produced in Pakistan is actually used by induction machines. So induction machines we are going to talk on. And since I'm using the word machine every time now, I guess machine topic, whenever I'm using the word, this means that I'm referring to a motor as well and a generator as well. So when I'm talking about the motor and generator, I'm going to use the common word machine. And just to clear one concept, every machine which can run as a motor can also work as a generator. There can be some limitations based on the output power or some losses or whatever. So even if you're at your home or at your classroom, if you have a fan revolving on your roof, on your ceiling, sorry, so if that is rotating by giving electrical energy, you can give mechanical energy to that fan and take an electrical energy and output. There can be some limitations based on what type of power, what losses, or what efficiency you can achieve, but every machine which can work as a motor can also work as a generator. So whenever I'm talking about the word machine, it refers to a motor and generator. So when we will talk about the induction machine, we will also talk about the induction generator, because induction generators are the workhorse nowadays, and they have found their usability in wind turbines. Wind turbines, which are going to be, they have recently been installed in Pakistan in this Sindh belt. We have a wind corridor over there in the Sindh. So normally the wind corridor has been found to be approximately 10,000 megawatt, which is a very huge number. But induction generators are the main stream working over there. We will talk a full lecture on this one, induction generator, how the gear mechanism actually changes the 3 to 9 meter per second airflow in that wind corridor, and through some gear mechanism this is converted into some instantaneous power which is going to be transferred to the grid. Now when I'm talking about the word grid, since I have talked previously on this grid topic in my live lecture also, grid is actually that part of that system which is going to be having at least a voltage of 133 kV plus. Now in since it's an underdeveloped area, so the word grid is not existing over there. The reason, they don't have any people over there which can actually consume power. But if you take the condition of Lahore or anywhere else, we have approximately 75 to 80 grid stations in Lahore. So approximately we have 133 kV lines coming in. It can be more than that also, but 133 kV is the normal voltage coming in any grid station in Lahore, on those 70 to 80 grid stations in Lahore. So this means in Sindh, the grid is non-existent. So normally at present, my information is this, that the energy that is being produced by the induction generators, which are working as wind turbines over there, that is going to be utilized by their own local loads, but it's not being fed into the grid. So normally, I guess what information I have at present is this, that a 50 megawatts power plant is there, which is having approximately 5 or 10 wind turbines, which means that it's a cluster of 5 or 10 wind turbines producing approximately 50 megawatt. That's a peak power. Certainly it will be changing throughout the day, just like the solar energy, it changes throughout from in the morning at 6 or 7 p.m. in the morning to 5 or 6 p.m. in the evening. Similarly, wind has a different characteristics. In the morning, it will be different. At night time, it's going to be different. But it is available 24 hours a day with intermittent ranges. So we are going to talk a lot on this induction motor, induction generator in detail, how you are going to run a three-phase machine. Here I have drawn these three phases, and I hope you have done this three-phase inside your CAD course, and even if you have not done it, you must have an idea for your CAD 2 course, which is also going simultaneously with this course of EMF at present over here. So this will be the three phases, how these three phases are working, and how their peaks are actually having a 120-degree phase displacement over there. We will discuss them in much detail over there at that time. Then the fourth CLO, if you see over here, the word used is synchronous machine, that is assessing the operation of synchronous machines in a power system. So synchronous, I'm not going to go in deep over here. What does the word synchronous mean over here? But just to give you a little bit idea, synchronous machines are those machines which work at a constant speed, which means that if you want to run them as a motor, you have to give them a constant frequency. And if you want to run them as a generator, you can get a constant frequency as an output, that is the AC voltage available from those generators. And these are actually the workhorse of any power system in any country. In Pakistan, you already heard the word Mangla, Tarbela, Capco, the recently added Sahiwal core power plant. So these two or three different, or many in fact power plants, they are having a different power source, but their motor or generator, in fact generators, because they are power plants, they are actually producing mechanical to electrical energy. If I'm talking about Mangla or Tarbela, this means I am converting that water hydel energy into electrical energy. So, but if I'm talking about Sahiwal coal power plant, then it means that it's actually burning coal and then running a steam turbine over there, and that steam turbine is actually curving. Word turbine or prime mover, I hope this is a little bit clear at present, that word turbine or prime mover is actually going to be a mechanical source for your generator. So we'll discuss in very much detail the see, that's why it's actually having a CLO4 over here. So we will talk about the power system, how power is fed from these generators, and then we will talk about a little about the synchronous motor, because synchronous motor is one of those motors which has almost no speed change whenever it is running at any load, unless and until that load can be lifted by that machine. Then these are the four CLOs. I guess this is a little bit of detail. And then our course is going to be mostly having very much deep analysis on the voltage and frequency relationship. Remember, in Pakistan, we have 50 hertz. Now, a question may be coming in your mind that why we have that 60 hertz in US or maybe anywhere else in any other country. The reason is very simple. At that time when Edison was actually very vocal on his DC bulb, the only load source at that time was a DC bulb and everyone wanted to run it. Now, at that time when DC was prevalent, they wanted to actually test AC. At that time, the induction machine that was producing the AC voltage at that time, it was producing they tested four different frequencies at that time, and those frequencies were 15, 30, 50 and 60 at that time. That was the maximum frequency available. So when this was being discussed at that time, some of the scientists at that time, they found out that 15 and 30 was a little detrimental for the patients of epilepsy, and it was having a flickering effect over there, in certainly at 50 hertz or 15 hertz. So then some of the scientists at that time, they took 50 as it, and some of them went a little bit above and then went on to 60. And nowadays the system is fixed. So now in Pakistan we have a 50 hertz because we have been under the British rule for a very long time. So the system which has been erected over here is 50 hertz, and then if you see in the US, it is approximately 60 hertz. Now a question may arrive in your mind that now can we change it, because now we are an independent nation, and now if we can want to change it back to 60 hertz so that we go on towards a different system. So but that is not possible. Why? Because all the transformers, all the machines which are erected in our system, they are working at 50 hertz. So frequency is a very, very critical factor. We will prove it with some equations over there, that now you cannot change the frequency. Now we have to live with this, or unless and otherwise we change all the transformers, all the fans, all the loads. And one thing, just to give you a little deep analysis over there, if you change your frequency from 50 to 60 hertz, your inductance remains the same, but X is L, which is actually the inductive reactance, that goes on to 2 pi FL. Now, if you can see, F increases from 50 to 60, this means you are increasing the XL by 1.2 times, which is actually a 20% increase. So what will happen? The current that is flowing inside your machine, because it's an inductor, every winding that is inside any electromechanical device has an inductor inside it. So when that XL is increasing, the current is going to decrease, and when that current is going to decrease, the amount of flux being produced is going to be decreased. So the amount of power that can be generated from that is going to be decreased. So technically, you cannot run a 50 hertz device on 60 hertz. Maybe it can run with little changes, but as such, its power parameters or performance parameters are going to be changed over there. Just a little statement over here regarding frequency, that nowadays when science has evolved, Now 400 hertz is the optimal frequency. Scientists have found out that 400 hertz is the optimal frequency for any power system. And but now we can't go on from 450 or 60 hertz to 400 hertz. But nowadays, if any of you has an interest, all aircraft engines, maybe Boeing or Airbus or any other even fighter aircraft, they have a 400 hertz generator on them as an auxiliary generator or a standby generator also over there. So 400 hertz is the, but when we will talk about this frequency parameter in much detail. Now this course is going to go, we are going to cover the CLO1 and CLO2 much before your midterm, and the CLO3, which is actually related to transformers, half part of that CLO is also going to be covered before the midterm. Now transformers, we are going to make its equivalent. We are going to talk on the equivalent circuit or the equivalent over here, and then that same model we are going to copy it for a three-phase induction machine. We will discuss it why it is like this. So after the midterm we will be having a three-phase induction machine or maybe a little portion of transformer if it's not complete, and then we will be talking about the synchronous machine, the CLO4. Now before the end of this semester, approximately 3 to 4, and hopefully we are online, we will be having some presentations in our lab timings or maybe some tutorial class. We will arrange that time over there. If supposingly you are 45 in number in each section, assuming I have approximately 99 student strength in LMS. So assuming even if you are 100, I will make a group of 4 students per each group. So I will have like 12 to 13 topics. Now what are these topics? I will give a list of at some appropriate time. They are based on some small motors, which are stepper motors, brushless DCs. All of you who are a little bit enthusiastic about EV vehicles or electric vehicles, they are now more prevalent. The BLDC machines, the brushless DC, as the name suggests, it's a DC machine, but it works on a little bit AC principle, and it is brushless, which means there are no carbon brushes over there. Then we will talk, then will be some topics such as pole shaded motor or induction generator. There are some classes of it that are either the 3rd class or the 4th class. So we will talk on that much. So there will be like 12 or 13 topics, and we will decimate those 12 or 13 topics to the groups in each section. And then you have to actually give a simple 10 to 15 minute presentation on that topic. So that topic has to be kept in those 10 to 15 minutes, and that presentation will be taken as some performance in your lab part or your theory part. Remember one thing, please directly correlate the lab and the theory one, which is very much important, so that your learning is at its maximum. Now we have discussed this DC motor over here just as a little brief overview, because you already know the DC machine done in your FSC or your A levels. So what I have drawn over here, as you can see over here, I have 2 permanent magnets. They are curved magnets over here, north and south pole. And you can see very easily that this north pole, which is over here, is giving rise to some flux lines, and those flux lines are traveling towards the south pole. Now remember, whenever there is going to be a magnetic field, that magnetic field is going to be always flowing from a north pole and flowing on towards the south pole. So if it's a 2-pole machine, I have drawn this north pole and south pole, and in between it I have a simple loop over here. And what this loop is there, this loop is going to have an DC current flowing through it. This is a DC motor. You have seen this diagram before also in your FSC or A level classes. So this is a simple motor with a single loop presented in between 2 electromagnets over there. Oh, sorry, 2 permanent magnets. Electromagnet will come a little later. So these are 2 permanent magnets over here. And you can see very closely over here that the loop, I have named it as ABCD. Now what this is ABCD, this is actually telling me that when a current is going to travel, segment AB, BC, CD and DA. DA is actually bifurcated in 2 segments over here, but still it's there. So the segment AB, it's having a current. Now this is a 3-dimensional diagram, a single one. So what is happening over here, the current is going inward of the board over here, or my screen at present. So that's why I have written it as a cross over here. You can see the conductor I have shown over here, it's having a cross, which means the current is going inward of the board. in front of you. And when in segment CD, the current is actually coming out of the board, it's a three-dimensional picture, so that I have shown it by a dot. Now this is just going to be a universal convention I'm going to use through this course. So now this is a motor. You have a current flowing inside this segment from A to B, and then from B to C, then from C to D, and then from D to A, and then completing the path. Now segment BC and AD, they are not going to develop any force. Now, I don't know how you have actually done this in your FSC or whatever, but the rule which is actually used over here is called as the Fleming's left-hand rule. Now, Fleming's left-hand rule, if you, I'm showing you over here in this diagram, you can see that if you use your left-hand rule, the fingers in the same direction is pointing out the magnetic field. The current is perpendicular to that magnetic field. If it is flowing, the thumb pointing out, it actually gives the direction of the motion that conductor is going to experience. I'm repeating it again. This is the Fleming's left hand rule. You have to use the left hand. The fingers in the direction of the hand are the P, that is the magnetic field flux lines, and I is perpendicular to the angle over here at 90 degrees, and the motion. So all three vectors are at 90 degrees to each other. So over here, if I draw this one on this conductor AB, so I have drawn this one over here, you can see this is current I going inward of the board. B is flowing from north to south, and these are at 90 degrees to each other. So the segment FAB, if you use your left hand rule and you apply this over here, you can find out the thumb is pointing out downward. So this is that FAB which is acting on it. And if you apply the same thumb rule, left hand rule on segment CD, where the current is actually coming out, so you are going to get the force in the upward direction. So these two forces, they are going to combine together, and they are going to give rise to a couple of forces which is going to rotate this loop in anti-clockwise or counterclockwise direction. Now the segment BC and DA, they are not going to develop any force. Why? Because the direction of current and the direction of magnetic field B, either they are parallel or anti-parallel. What I mean by parallel means that I is flowing in this direction, B is also flowing in this direction. And by anti-parallel, I mean that current is flowing in opposite direction, B is flowing from left to right. So what is happening over here, if you remember your elementary classes, the formula for the force F was equal to I into L cross B. That was a vector product over there. So now when the both vectors are already in that, so when you are going to have that angle, so this angle is 0 or either 180 degrees, the force will not be produced. So segment BC and DA, they are just completing the path over here. So there is not going to be any force. But again, these two forces, FAB and FCD, they are going to actually give rise to a couple of forces, and the loop will start to rotate if there is certainly some axis of rotation with the help of some bearing. Now, when this will rotate 180 degrees rotation, what will happen over here, that after completion of 180 degree of rotation in the anti-clockwise direction, as I have shown over here by this yellow color arrow, when it will complete it, the direction of current in the loop has to be reversed. And for this purpose, I have attached over here a commutator or split ring. Now this is called as a split ring because you can see this is in purple color over here. And this is just a simple ring cut in two halves. One half is hard coded to one end of the loop, other one is hard coded to the other end. So when it is going to complete 180 degree of rotation, it's going to reverse its contact with the two carbon brushes over there. So this is the commutator segment, and these are the carbon brushes. I hope I'm going to use some abbreviations over there. So carbon brushes, I'm always going to use CB. So these carbon brushes, and I don't need to repeat it, the carbon brushes are being used over here because they are better in erosion. So they can constantly have that wear and tear and still conduct that electricity through it. So this is connected with a simple DC supply, as you can see over there. So after 180 degree of rotation, the carbon brushes will come in contact with the opposite side of the split ring. So now the current direction will reverse. Now if this does not happen, supposing you don't need or don't have a commutator or split ring, and you hard code it to whatever mechanism over here by using some other mechanism, I will show you that picture later on when we discuss DC machines in a little bit more detail. So when you are going to have that hard coded, the machine is not going to give you any rotational motion. Reason, that it will have a flip-flop, which means it will complete 180-degree rotation and then it will come back again to the same equation, then it will again go on. So practically it will not be a rotational motion, it will be a vibrating motion, 180 degrees, then minus 180 degree, 180 degree, then minus 180. So a commutator or a split ring is very much important for any DC machine to work it. So this is the normal working of any DC motor. Now, a question may arise over here that magnetic field lines which are flowing from over here north to south pole, from south pole they have to return back to the north pole. So what is going to happen? I have just shown you a small cut piece view, a 3D view of this motor over here. But in practical, the south pole will be connected to the north pole through a longer path, which I'm going to call as yoke, which is still not shown in this diagram. That since this is a three-dimensional diagram, what I have drawn over here, if I just scroll down a little bit over here, this is a 2D cut view or a cross-sectional view of our DC motor over here. Now you can see I have shown the two poles over here, which are shaded over here. So the two poles you can see over here, these are two poles over here, this portion and this portion. So the two poles over here, and there is some winding now on it. Now instead of using permanent magnets, because permanent magnets, they will lose their magnetism after some time. So certainly I will have to have a little better mechanism of producing magnetic field. Remember, there are always three conditions for mechanical motion to actually be produced. First one, you need a magnetic field. Second one, you always require a current carrying conductor placed in a magnetic field. So then you are going to have, so the three conditions, if I name them again, you need a magnetic field, you need a conductor placed in a magnetic field, and thirdly, you need a current flowing through that conductor. Then these three conditions are fulfilled, you will have a mechanical motion produced over there. So overall in this diagram, as you can see, the magnets have been replaced by poles, and on those poles I have made a small field winding, and on this field winding you can see I have connected them in series, and I have shown some arrowheads also for the polarity, which is actually the magnetic field being produced over here. So you can use the right hand thumb rule with your fingers around the winding current direction and the thumb pointing out in the direction of the magnetic flux. So what will happen over here, that the south pole is on top over here and north pole is on bottom. You can use your right hand. Please remember, this is the right hand thumb rule, which means that the fingers are curled on the winding in the direction of your magnetic, the current direction, and thumb points out in the direction. So here in this view, what is happening, the lower pole is the north pole, from where the flux lines are going to go towards the south pole. And you can easily see these dotted lines, the gray dotted lines, the flux lines are going to flow from the north poles to the south pole, passing through the rotor. Now, when it is going to reach the south pole, they have to return back to the north pole. Now, if this outer part, which is actually yellow shaded over here, which is now going to be called as yoke, if this is not present, the flux lines have to come through air. And you all know air is not a very good medium for magnetic flux transfer. So this means that magnetic flux has to travel through some good material, and that material has to be ferromagnetic in nature. So this yellow color portion, the outer covering of your machine, which is again stationary, is called as the yoke over here. So yoke is a very important integral part of your machine. If yoke is not there, the flux path cannot be complete. So over here, if you can see the outer part of this machine, and if I name now two portions of your any machine, one is called as the stator, the other one is called as the rotor, and I don't need to explain this. The stator is for the stationary parts, rotor is for the rotating parts. First, if we talk about the stationary parts over there, we just talked about the poles, and they had to be ferromagnetic material or some material that can actually assist in magnetic flux flow. Certainly not plastic or some wooden. It has to be some silicon steel or some other material which is good conductor of magnetic flux. And then this current, this flux flows through it, passing from the rotor, reaches the yoke over there. So now in stator, you can see that I have a permanent magnet or poles, which means, and then there is going to be field windings. The windings, because this time I am using an electromagnet. Electromagnet has to be there. Then there is the yoke, which is actually the outer part of your machine. And then the stator portion also has the carbon brushes over here, because carbon brushes are also going to be stationary. Now, if I move on towards the rotor, in the previous diagram, the three-dimensional, I showed you that the rotor here was just a single loop over there, and that loop was just a simple coil. Now that coil, if it is placed just in simple air with some mechanism of axis of rotation, flux lines have to pass through it. Now flux lines, they again passing through air, it will not be a good medium. So what we do, we take a rotor core, some ferromagnetic material again over there, and we put those conductors inside those core, which means actually practically if I have something like this cylinder, and in this cylinder, if I just zoom it a little bit over here and I change this one, so what I am going to do, this is going to be the loop placed over here like this. The other end of the loop is going to be here, and it's going to be connected from the back end. So now this loop over here, or this cylinder, this is the cylinder placed over there. So this is a three-dimensional view of that single loop. So now when this is going to be placed inside the stator with minimum air gap. What is air gap over here? This air gap distance between the poles and the rotor is going to be called as the air gap, and smaller the air gap the better, because air again is involved. You can't reduce it to zero because it's a moving part. You cannot have it always rubbing the stator poles, otherwise mechanical damage is going to be there. Now over here in this cut view diagram, you can see I have installed not just one loop, I have many loops over there. In fact, if I do a little bit counting over here, this is loop number 1, 2, 3, 4, 5, 6. So what I have done, I have 6 loops arranged in the whole 360 degrees over there. So this is 1, this is 1 dash, this is 2, this is 2 dash, this is 3, this is 3 dash, this is 5, 5 dash, 4 first, and then this is 5, and this is 6 dash. So now I have 6 loops over there. Now these 6 loops are going to be connected to the supply again through some commutator. How that commutator would be, this time it won't be a simple split ring, or it will be more split rings into like 6 or 12 halves over there. We will discuss when we have a winding design in front of us. But overall, the advantage of adding loops over there is this, that now because of their series and parallel connections, which will be based on some winding, it will give rise to a more forces which was inside the motor. So now the torque which is going to be produced, and we all know torque is equal to R cross F, where R is the moment arm and torque is the total torque produced over there. So now this time when there are 6 loops are going to have those 12 forces produced. Maybe they are having a little different force because of the angle over there, because I've told you F is equal to IL cross B. So now when this force is going to be added up, your total force of this whole motor is going to be more as compared to a single loop over there. So now when that single loop is going to be there, the force being produced by those 6 loops is going to be very much high, and the motor is going to give you a lot amount of torque over here. So this is a simple view, and if I make the rotor view or rotor parts over here, the first part, as I told you, since you are using a ferromagnetic material, so now when you are going to have a 3-dimensional view or something like that, you are going to have coils arranged in, this is the whole length of that conductor. You can call this is A, this is B, and then this is C, and this is D. So there will be like 6 coils arranged over here like this on the surface or inside the cylinder. We will talk in much detail how this will work. So this is 1, 2, 3, 4, 5. You can add the 6 ones yourself. So in the rotor parts, you have the rotor core on which all these windings have to be done. And then the rotor winding, certainly, that is the loops over here. In this motor, I have shown you just 6 loops. It can be even 100 loops. So for big machines, it can be 100, 200 loops over there. All those loops, greater the number of loops, the difficulty increases for the winding design, but also it increases for the amount of torque being produced over there. And vice versa, if this machine is working as a generator, it can work as a generator also. You are giving mechanical energy to the rotor shaft, so you are going to get lot amount of electrical energy as an output. So more winding means if they are connected in series, which means more voltage. If they are connected in parallel, you are going to get more output over there. This is going to be a generating source. The third thing, it can be a commutator, or it can be a split ring. What is a commutator, or what is the difference between a split ring, we will discuss in much detail afterwards. But just for now, these are the parts of a stator and a rotor, and which are of our concern especially. I'm not talking about the mechanical parts over here. The mechanical parts certainly would be the outer casing, the bearings, the shaft of the machine, and any other mechanical assisting parts which are going to be there assisting the carbon brushes or the springs or whatever. So they are the mechanical aspect. I will show them in some picture in next lectures to go on. But just over here, you have seen the 2D cart view and the three-dimensional single loop placed between a north and south pole. So I hope this is clear over here. I've just given this a little bit fresher over here so that the concept of DC motor, which we have already visited in your previous classes, and hopefully I guess in physics and magnetism course you must have visited all this. But here from the motor's point of view and the Fleming's left hand point of view. So in the next class we are going to talk on chapter number 1, Chapman, edition number 5th. So signing off up till that time. I hope you have enjoyed this.